As you can see from the title of this lesson, this is a tutorial on gas stoichiometry where we are changing the identities of substances. This is an idea that we tackled already once this year, which led off the stoichiometry portion of what we do in this class. First thing you have to understand is we are talking about the types of problems where we have to write and balance equations and use a mole-to-mole ratio to change from one substance, say sodium oxide, to a different substance, say sodium bicarbonate. We can do the same thing with gases, except now we can add in this portion about knowing 22.414 liters, and we can convert volumes of gases into moles and change identity. Or if we don't have standard temperature and pressure, we can use the ideal gas equation to get moles and go ahead and find a new identity of a substance. And if you print out the notes for this particular topic, right, you'll find that they're called gas stoichiometry examples. They're number 5 in the notes section. Right? And if you look back into your notes into chapter 9, it will give you a quick 4-step method to solving a stoichiometry problem. Right? As a reminder of what those 4 steps are, first step says to write the problem. What do I know? What am I trying to find? Make sure you have labels on it. Second step. Predict products. If you need to go back and use your note card again, you can do that. Right? But when we predict products, we're talking about looking at our signature characteristics of different things. Synthesis, element plus an element. Decomposition, no plus signs. Single replacement, element plus a compound. Double replacement, compound plus a compound. Combustion, hydrocarbon, where I have to give you the formula, plus oxygen. So you predict those products. Right? Step 3. Write and balance an equation. And lastly, step 4. Get yourself the moles as quickly as possible and use the mole-to-mole ratio to change your identities into whatever it is that you want. If you take a look at the examples, the first one that we're talking about says, how many grams of calcium carbonate will be needed to produce 5.00 liters of carbon dioxide gas at STP? If I were trying to solve this problem, first thing I do is I list what I know. And it seems like I know that I have 5.00 liters carbon dioxide at STP. It says how many grams of calcium carbonate will be produced. So we're going to grams of CaCO3. A lot of times here I ask, are we changing identities? And here's what I mean. CO2 to CaCO3, that is a change in identity. Like, the only way we know to change from one substance to another is by linking them in an equation and using the mole-to-mole ratio to change it. So we go into the question and we underline things that look like they belong in a chemical equation. The 2 things that stand out are calcium carbonate and carbon dioxide. Then what we do is we cross out any of the ones that look to be products. And that would leave us with calcium carbonate. Only one type of reaction is characterized by having one thing with no plus sign. That's a decomp. We would go through our checklist. Is it a chlorate? No. Is it a carbonate? Yes. Right? So if it's a carbonate, metal carbonates break up into metal oxides plus carbon dioxide. All right, so we're talking about calcium oxide and carbon dioxide as our products. Now we write in balance. Calcium carbonate is CaCO3, calcium oxide, CaO, carbon dioxide, CO2. You'll find that it's already balanced, 1 Ca on both sides, 1 C, and 3 O's. Anytime you're going to try to do a problem like this, it helps to set up a game plan. Right? So we are starting in liters of CO2 at STP. I say we want to get to moles as quickly as we can. So our goal is to get to moles of CO2 to start. Because we're at STP, that's a one-step problem. We use the 22414 to change it. Once you're into moles of what you know, you can change the identity. And we're trying to go to the CaCO3. Again, that'll be a one-step. This is why we had to write and balance an equation, because the equation links the mole-to-mole ratio. Once I'm into moles of what I want, I can get to whatever unit that I want. In this particular instance, we want grams. So that'll be our plan of attack as we go through. So I'll start with my 5.00 liters at STP of CO2. First thing I'll try to do is get into moles. Liters CO2 on the bottom, mole CO2 on the top. This is at STP. Because we're at STP, 1 mole has 22.414 liters. Once I'm in moles of CO2, I'm able to change my identity. Moles on the bottom, moles of what I want on the top, which is CaCO3. Notice, using the blue marker, because that refers to the equation up here, that is a 1-to-1 ratio. Lastly, I can convert moles, CaCO3, into grams, CaCO3. We do that all the time. 1 goes with mole. If we add up CaCO3 from the periodic table, you will get 100.09 grams. So if I take out a calculator, okay, 5.00 divided by 22.414 times 100.09, you'll get a number of 22.3275, 3 sig figs, 5 sig figs, 5 sig figs. I get 3, so 22.3 grams CaCO3 would be needed. Right? Question, strategy, or write and balance the equation, because you'll need it. Write and balance the equation, bracket problems. So long as you're at STP, you'll be able to solve everything with a bracket problem. When we get to non-STP conditions, you'll have to start to use the ideal gas equation, because we won't be able to use the 22.414 to convert to moles. Example number 2. 2 says, given the following reaction, S plus O2 yields SO2, how many grams of elemental sulfur are needed to produce 12.61 liters of sulfur dioxide gas at STP? You're going to try to follow the same system. The reason being, right, take a look at what you were given. Right? You were given liters of a substance. We were given liters in the last problem. You're asked to find grams of a substance. We were asked to find grams. So these problems should be structurally very similar. First thing I do is list what I know. I know I've got 12.61 liters of sulfur dioxide, SO2, at STP. I want grams of elemental sulfur, which is grams of S. All right. Sometimes the equation will be given to you. You don't have to predict right and balance. And that is the case here. You were given an equation that tells you what our second line there was. So we can do our game planning strategy and then list our equation. So we have liters of SO2 at STP. I always say, get to moles as quickly as you can. So you go to moles of SO2. We can do that in one step because we're at STP. Moles of SO2 lets us change identity to moles of S. Moles of S then to what we want, which is grams of S. All right, now we're ready to rewrite our equation, which said S plus O2 yields SO2. Start with what we're given. 12.61 liters SO2 at STP. First thing I want to try to do is get it into moles. So I put liters SO2 at STP on the bottom, mole SO2 on the top. Okay, that 1 mole has 22.414 liters. Once I'm into moles of SO2, I change identity. Mole of SO2 to mole of S. This is again a 1-to-1 ratio. Now that I'm in moles of S, I can go to grams of S using the mass from the periodic table, which is 32.07. So now we'll do the math portion. 12.61 divided by 22.414 times 32.07. Looks like I get 18.0424. 4 sig figs, 5 sig figs, 4 sig figs. So I will call that 18.04 grams of S. Very similar problem. Number 3 changes a little bit. All right, 3 says carbon monoxide reacts with excess oxygen to produce carbon dioxide. If 1.0 liters of carbon monoxide reacts with oxygen, there's 2 questions. How many liters of oxygen are occupied at STP? And how many liters of carbon dioxide are produced at STP? Don't try to solve both questions at once. Do them one at a time. So the first thing I'll do is I'll list what I know. It seems that I know I have 1.0 liters carbon monoxide at STP. Next thing I know is that I'm trying to find liters of O2 at STP. So let's set up a strategy. First thing, I'll start with liters CO at STP. First thing I want to do, get it to moles as quickly as I can. So we'll go to moles CO at STP. Shouldn't be a problem. We can do that in a bracket. Once I get to moles, I can change identity. Mole CO will go into moles of O2. And once I'm into the identity of what I want, I can change into the unit. The last couple times it's been grams, but this time I want to go into liters of O2 at STP. Because I am changing identities, right, I'm going to have to write and balance an equation. In this case, they tell us Carbon monoxide, I would pull that out. Reacts with oxygen, I would pull that out to produce carbon dioxide. I would cross out the carbon dioxide because it's a product, and I would get carbon monoxide plus oxygen. This one's a little tricky because we have a non-metal with a non-metal, right, which tend to be not replacement reactions. They tend to be synthesis, and we don't cover that too much in Gen Chem. That's why I gave you the products to be carbon dioxide. But if I give you the reactants and the products, you should be able to, right, convert those things into their formulas and write and balance an equation. Right? Carbon monoxide is CO. Oxygen is a Hoberfinkel, O2. Carbon dioxide, CO2. To balance this, looks like you put a 2 here and a 2 here. Now we're ready to do our problem. So I start with my 1.0 liters CO at STP. First thing I do is change that into moles. Because we're at STP, that's a one-step bracket problem. Liters CO on the bottom, moles CO on the top, 1 to 22.414. Step 2, moles of CO to moles of O2. Using our mole-to-mole ratio, I think you can see that there's a 1 in front of O2, there's a 2 in front of CO, so we use a 1 to 2 ratio to make that happen. Then we go moles of O2 to liters of O2. And those liters are at STP, so I can say 1 mole has 22.414 liters. You plug this into your calc, you end up getting 0.50 liters O2 at STP. Second part of the problem, you don't have to do a bunch of new work, so to speak. Right? In the second part, they're asking you to find the liters of carbon dioxide. So you don't have to repeat all of this. Right? Your question will be 1 liter CO to CO2. One thing I want to point out is if you look right here and here, these first and last brackets undo each other. They cancel. Okay? That will happen anytime you're going liters of a gas to liters of a gas at STP. We learned about a law at the beginning of a chapter that says we can treat gases the same way as we do liquids and solids, meaning use the mole-to-mole ratio. The difference is we can just call it liters and use the mole-to-mole ratio because the only part that mattered in that problem was the middle part. So for this second part, letter B, we'll go from liters of CO to liters of CO2 at STP, and we will just use the mole-to-mole ratio. CO has a 2, CO2 has a 2. And you'll end up getting 1.0 liters CO2 at STP. Right? You could have done it the same way as you did here. 1 mole, 22.414, 2 over 2, and then 22.414 over the 1 mole. Either way, it will work. Choose the way that makes the most sense. But if you're going liters to liters at STP, it is perfectly all right to do the mole-to-mole ratio in with the liters. Right, so those are 3 examples of problems that are done at STP conditions. Let's take a look at some problems and how they work if we are not at STP conditions. For instance, number 4 says, how many liters of chlorine gas will be needed to react with 10.4 grams of sodium bromide at 38 degrees Celsius and 1.63 atmospheres? If I'm going to figure out a problem like this, we will do it the same way as we've done all the others. List what I know, list what I'm trying to find. I know I've got 10.4 grams of sodium bromide. And I am trying to find liters of chlorine gas, which is a Hoberfinkel, at not STP conditions, which are at 38 degrees Celsius and 1.63 atm. Temperatures and pressures are always conditions that go with volumes. That is why I link them together like this. The grams is always at STP, so I don't worry about the conditions being with this, even though they're numbers. So if you take a look at what we're going to try to do, I am currently in grams of NaBr. I always say get to moles as quickly as you can. Right? So we can go grams to mole in one step. Once we're into moles, we can change identity. Once you reach here, once you get moles of Cl2, you want to go to the liters of Cl2. Right? When we were at STP, that was a bracket problem. Now that we're going to liters at not STP conditions, just like in the other types of problems we were doing, if you are at conditions other than STP, it is best to use the ideal gas equation. Get yourself moles. We want liters at a temperature and a pressure, so we will get ourselves to that by using the ideal gas. Because I'm changing identities, I need to figure out my reaction. If I take a look, it says chlorine and sodium bromide. Neither of those say will be produced, so I have both of those as reactants. If I were to look at that, I would see that it's an element plus a compound. That means a single replacement. Chlorine is a negative, sodium is a positive, bromine is a negative. So chlorine and bromine will trade places, leading me to sodium chloride plus bromine. Remember, single replacements, check your activity series. Chlorine is higher than bromine on the table, so it's okay to do that. Chlorine is Cl2, sodium bromide, NaBr, sodium chloride, NaCl, and bromine is a Hoberfinkel, Br2. Have to balance this thing. 2 Cl's on the left, 1 on the right, so I put a 2 there. Na changes to 2, so to fix it, I put a 2 there, and that balanced the bromine. Now we're going to try to solve our problem. I start with what I'm given. I want to change it to moles as quickly as I can. So, grams of NaBr on the bottom. Mole, NaBr on the top. One goes with moles. I go to the periodic table and I get Na and Br. Na is 22.99, Br 35.45. Add those together and you get 58.44. Now we're trying to go from moles of NaBr 2 moles of Cl2. That's a mole-to-mole ratio from my balanced equation. There's a 1 in front of the Cl2, and a 2 in front of the NABR. Now, here to go from moles to liters, right, there's one of two things that you could do. You could go moles to liters using the 22.414, and that would be liters at STP. Then you could do a combined gas law problem, right, to change it into liters at your conditions. Right? You could also go there directly using the ideal gas equation because you'll have moles here, right, and then you can go to liters at any conditions using the ideal gas. Right? We're going to do two problems. Right? In the first one, right, I will take us to using the ideal gas equation. In the second, we'll do the combined gas law. So because the ideal gas equation needs moles, we'll stop here and we'll get ourselves an answer. And so 10.4 divided by 58.44 divided by 2 gets me a value of 0.08898, right? And with 3 sig figs, 8898 would become 0.0890 mole Cl2. I want to go from the moles to the liters now at conditions, right? So I have one piece of what I need for an ideal gas equation. Ideal gas equation says PV equals nRT. In this problem, I want the volume, so I'm looking for liters. So I divide away the P, I get V equals nRT over P. Before I plug in, I always ask myself two questions. Right? Do my units match? Is my temp in Kelvin? Right? So if we take a look, do my units match mean, do they match the constant R? And you can always plug R in right away. 0.0821 liters ATM per mole Kelvin. So N would get plugged in first. That's our amount. It has to be in moles. We just found the amount in moles. So I can plug the 0.0890 moles Cl2 in there for the N. Okay. R we already have in there. T is the temperature. And with the temperature, it has to be in Kelvin. Here is my temp. It's not in Kelvin, so I have to change it. 38 plus 273 is 311. Last but not least, right, I want my pressure. Pressure has to be in ATM. And sure enough, the conditions they gave us was an ATM. So 1.63 ATM. And so it seems like I have everything I need to plug in and solve for my volume. Atmospheres will cancel. Kelvin cancels. Moles cancel, leaving me with liters at our conditions. And I plug in and I do my math. 0.0890 times 0.0821 times 311 divided by 1.63. When I do that, I get a value of 1.39 liters of the Cl2. Right, so very similar, right, system. Get yourself the moles as quickly as you can. Change identity using an equation. Now, because we're trying to go to conditions not at STP, we can use an ideal gas equation to get ourselves our volumes right in one step. Let's take a look at number 5. Number 5 says, how many grams of carbon must be burned to produce 2.53 liters of CO2 at 20 degrees Celsius and 732.5 mmHg. First thing I'll do in this problem is list what I know. By looking at the question, it seems that I know I've got 2.53 liters of CO2 and because that's a volume, it gets conditions. The conditions on that are 20 degrees Celsius and 732.5 mmHg. I am trying to find how many grams of carbon must be burned. Grams of carbon. So first thing you do is say, am I changing identity? And the answer to that question, CO2 to C, is yes. We are changing identity. So we set up our game plan. I'm in liters of CO2 at 20 degrees and 732.5 mmHg. I try to get to moles as quickly as I can. Because CO2's not at STP, the easiest way to do that is using the ideal gas equation. Once I'm into moles of CO2, I change identities. Moles of CO2 into what I want, which is moles of C. And then moles of C into what we're looking for, grams of C. So, to do this, I'm going to need a balanced equation to figure out what's going on. Right? So it says that carbon must be burned, right, to produce CO2. So if carbon is being burned, burned always hides oxygen. Again, this looks like it could be a combustion, okay, but it's not a combustion, right, because there's no hydrogen present, so we can't make water. It's a synthesis. They tell us it's making carbon dioxide. So you write and balance this down. Right? Carbon is C, oxygen, O2, carbon dioxide, CO2. Right. First thing I want to try to do is take what I'm given and get myself into moles. Well, I have liters, I have temperature, I have pressure. That is leading me to think that this is some type of PV equals nRT. Because I'm trying to get moles of the substance, I'm going to solve for N. I do that by dividing by RT. I'll get N equals PV over RT. Before I plug in, I make sure that my units match and my temp is in Kelvin. And so I always plop in R because it shows me my units. Liters ATM per mole K. So, first thing I would look at is my pressure. Right? Is my pressure in atmospheres like it needs to be? Right? No, it is not. It's in millimeters of mercury. So the first thing we have to do is convert our 732.5 mmHg into atmospheres so that we can plug in 1 ATM, 760.00 millimeters of mercury. If you plug that into your calculator, 732.5 divided by 760.00, you get 0.9638. We get 4 sig figs, so 0.9638 has a 1 after it. So 0.9638 ATM. My volume, according to our unit, has to be in liters. Sure enough, the 2.53 is in liters, so we can plug that in. Last but not least, temp has to be in Kelvin. It is not in Kelvin. Right, so we add 273 to that, which will just take this to 293. You do the math on that, 0.9638 times 2.53 divided by 0.0821 divided by 293. I get 0.101367. I get 3 sig figs, so I would say I've got 0.101 mole of CO2. Now that I have moles of CO2, I can start to change identity. And that gets us back into bracket problems. Moles of CO2, changing identity, mole CO2 on the bottom, mole C on the top. According to our equation, that is a 1-to-1 ratio. And then we convert moles of C to grams of C. 1 mole has 12.01 grams. So we do the math on this to finish up. 0.101 times 12.01. And we get a value of 1.21 grams of carbon. And so when you start to see these identity changing problems that are not at STP, you're going to want to involve some type of ideal gas equation where you get moles to begin a conversion, or you do conversions, get moles, and then convert it into liters using the ideal gas equation. I hope this helps with the changing identity problems that you're having. If it doesn't, please come in to see me for some help.